This section we talked about support vector machines. Support vector machine is a technique in which the decision boundary is represented using a subset of tuning points known as the support vectors. Given a dataset with tuning points, we need to find the decision boundary that separate the points from class to class, and this is one possible solution, and this is another possible solution, and another, and you may wonder which one is better, B1 or B2, and how do you define better? The discriminant function g of x is in the form of wt x plus b. W is the width vector on the decision surface. G of x is equal to 0. For a given point x, if g of x is greater than 0, then we classify x as the class 1. And if g of x is less than 0, then we classify x as the class 2. If 2 points x1 and x2 are on the decision surface, then we have this. And then we get to the product of W transpose and x1 minus x2 equal to 0. Here it means that W is normal with any vector in the hyperplane. Now we discuss the distance from a point x to the hyperplane. The distance from a point x to the hyperplane is given r, which is equal to g of x divided by the norm of W. And this is a proof. Let x equal to xp plus r multiplied by W divided by its norm. And this is the graphical illustration. The vector x is equal to the vector xp plus r multiplied by W divided by the norm of W. This is because from the previous slide we know that W is normal with the hyperplane. This vector is normal with the hyperplane and has a length of r. So we can express this in terms of W, which is r multiplied by W divided by the norm of W. Now we replace x into g of x. We have this, and have this, and have this. xp is located on the hyperplane, so g of xp is equal to 0. And finally we have just r multiplied by the norm of W. And from here we get the distance r, which is equal to g of x divided by the norm of W. From the result in the previous slide, the distance from the origin to the hyperplane is g at 0 divided by the norm of W, which is b divided by the norm of W. And the distance from the origin to the margin hyperplane, the margin hyperplane is parallel with the hyperplane. And similarly, the distance from the origin to the margin hyperplane is given by g at 0 divided by the norm of W. And g at 0 gives you b minus 1. And finally we have b minus 1 divided by the norm of W. And also similarly, the distance from the origin to the to the other merging hyperplane, and that is the other merging hyperplane. The distance from the origin to that plane is given as g at 0 divided by the norm of W, and g at 0 is b plus 1. And finally we have b plus 1 divided by the norm of W. So the distance between the two hyperplanes, the two merging hyperplanes, is given as 2 divided by the norm of W. Now let's look at the decision boundary, the separating hyperplane. For points x located on the separating hyperplane, g of x is equal to 0. For points x in class 1, we want g of x greater than or equal to 1. And for points of x in class 2, we want g of x less than or equal to -1. From the two conditions, we get to this. This form summarizes both conditions. We find the separating hyperplane such that its merging hyperplanes are maximally away from each other. So we need to maximize 2 divided by the norm of W, or minimize the norm of W. And that comes the optimization problem. We minimize the product of W transpose W subject to this constraint. With the Lagrangian multipliers alpha I, we convert the constraint optimization problem into the unconstrained optimization problem. The problem can be simplified by transforming the Lagrangian into a function of the Lagrangian multipliers only. This is known as the dual problem. We solve the optimization problem for alpha I. The points for which alpha I are greater than 0 are called support vectors. The vectors are critical elements of the tuning set. Once a set of alpha I are found, we can obtain the feasible solutions for W and B. What if the decision boundary is not linear? The discrete imminent function g of x is W transpose multiplied by x plus b. And from the primal problem, W is the sum of alpha I, yi, xi, and that's why we have this. Mapping the points xi to the high-dimensional space, we get the discriminant function g of x in the high-dimensional space. Here comes the kernel trick that handle the product of phi of x transpose and phi of x, which is point ith in the tuning set for I from 1 to n. This page shows several kernel examples.